Hello, I'm Anthony Steffen with Florida Institute of Technology, and today I'd like to discuss applications of linear algebra in ODE theory. This information comes from section 2.7 of your linear algebra textbook. We did not discuss this section in class, but it is very important, and the information that I talk about here, I'd like to show you a little bit of motivation of why we should discuss it. So it involves looking at finding solutions to linear, homogeneous, ordinary differential equations with constant coefficients. So we will look at how to solve an ODE, and then we will look at a specific engineering example that we can see in the real world. But then we'll get even more motivation to exactly how linear algebra steps in, organizes, and instead of finding just one solution to the ODE, it finds all solutions to the ODE in a mathematically systematic way. So with that motivation, let's look at our ODEs. This is a linear, we can tell it's linear because it only has y. Linear homogeneous ODE, homogeneous meaning that the right side is set to 0. Ordinary differential equation with constant coefficients. Beta is not to beta n are complex numbers. Okay, we can see that. Beta n cannot be equal to 0. Why? Because when we will solve, you will see as when we solve these equations, we'll want to divide by beta n. We can't divide by 0. Some of the notation that we'll be using is y in parentheses 1 will just be the first derivative of y with respect to t. T being time, our independent variable. Therefore, that's why it's ordinary differential equation. And y with j in parentheses will be the jth derivative of y, j being from 0 to n. So this equation 1 is our ODE. And I'll make a lot of references to 1 throughout the presentation. Every ODE can be associated with an auxiliary polynomial. This auxiliary polynomial here, okay, is in this form. As you can see the relationship between equation 1 and the auxiliary polynomial. Solutions to the ODE is by finding zeros, which we will denote by lambda sub j, to the auxiliary polynomial. So once we find these solutions, we can actually structure them, the special solutions to the ODE, as c sub j e to the lambda jt, okay, where cj and lambda j are complex numbers. So that would be our solution to the ODE. Let's look at a specific example, an auxiliary polynomial example. And this will also explicitly show why our beta n must be complex numbers. So let's look at this ODE here. We do see that it is of the form of a homogeneous, okay, constant coefficients. It is linear ODE. And it is going to be ordinary because we are only differentiating with respect to time. So this equation 2, just to show you explicitly the notation, we're taking the third derivative, second derivative, first derivative, and not taking a derivative of this y. Here is the auxiliary polynomial, equation 4. So when we're looking at this auxiliary polynomial, we can see that its coefficients are real coefficients. We have here 1, -1, 3, and 5. Okay, so when we try to solve for the zeros, our lambdas, we have here, I guessed that I could factor out a lambda plus 1, used polynomial division to find this polynomial here. So then therefore immediately we can see that lambda equal to -1 would be a 0 because it would make this whole entire equation be equal to 0, so that would satisfy it. Then to find the zeros for this other polynomial here, we can use a quadratic formula. As you can see, it doesn't FOIL out really nice. So when we use the quadratic formula, opposite of b plus or minus square root of b squared minus 4ac all over 2a, okay, we get within the determinant here, a negative 16. This negative 16 is the reason why our answer then, our 0, becomes a complex number. We have 1 plus or minus 2i, where I squared is equal to negative 1. So interesting that our zeros, okay, lambda 1, lambda 2, and lambda 3, are complex valued, although we have a real function. So those are the zeros. So let's look at the solution. So then therefore the solutions to 2, this ODE, are e, okay, 1 plus 2it, e 1 minus 2it, and e to the negative t, which we can see is just e to lambda 1t, e to lambda 2t, and e to the lambda 3t. Let's look at a more specific example, this mechanical engineering example. Okay, I want to look at a 1 degree of freedom, meaning in 1 dimension, spring mass dampening system with no forcing. Okay, clearly no forcing because the right-hand side we are looking at, currently we are looking at homogeneous ODEs. I like to mention that the example that's in your book isn't very realistic. They use a spring mass system without any dampening, meaning there's no resistance. So this term here would be gone. It's very unrealistic because it would oscillate indefinitely. So here we're looking at this equation. We can see immediately this is mass times the second derivative of y, which is just mass times acceleration. So the mass of that's connected to the spring. And then in addition to the resistance times the velocity, so whatever the resistance would be, plus k times y, so the displacement of y, k being this spring constant relative to Hooke's law. All right, so we can see that this is in the ordinary homogeneous linear differential equation with constant coefficient form that we want. Clearly, m, the mass, must be strictly greater than 0, and r and k could be equal to or greater than 0. All right, so when we divide by m, we put the ODE in this form of equation 6. We want to put this in an auxiliary polynomial because what do we want to do? We want to try to find the zeros to it to solve it. So we put it in our auxiliary polynomial. And then we need to look at the different cases. Clearly, we need to use the quadratic formula. Well, this term here, like we're always investigating, is our determinant. Okay, so if we are investigating the different cases, this case here is considered over dampening. Okay, meaning that yes, there would be a lot of resistance, but visually, what would this mean? It would mean that there would be exponential decay, okay, of the spring mass dampening system. Therefore, meaning if you had this system at, let's just visually think about this, if you had it at equilibrium and you had some type of displacement, once you released it, okay, the resistance is going to be very high and it's just going to exponentially decay towards equilibrium. All right. Then if we want to look at this critical dampening, this case 2 is where the determinant would actually be equal to 0. All right. So this case 2 is called critical because it's rather similar to the over dampening case, where if you want to visually think about it, where we're at equilibrium and we have some displacement, then this displacement is going to exponentially decay, but it's going to be maximized. So meaning that in the minimal amount of time from it going from displacement back to equilibrium is going to be maximized. And then under dampening is actually the case where there's not much resistance. So the third case, under dampening, okay, resistance is going to be lower. This here, we will see what kind of case this looks like in our solutions. But if we were to, let's say we were going to be at equilibrium here, and we were going to have some displacement, okay, from that spring, expanding it out, then when we let go of this here, it's going to go past equilibrium, and we're going to see a little bit of oscillation that would eventually result back to equilibrium. However, it does pass equilibrium, unlike these two cases. Okay. So case 1, when we're looking at this, okay, when we're looking at this case, the two solutions that we will get, okay, if you look at the roots of the auxiliary polynomial lambda, and here I put the quadratic formula up here so we can see exactly what we're looking at. Here, when this is greater than 0, okay, we're going to get two distinct roots. We're going to get them where they are real roots. Okay, case 2, when this is equal to 0, okay, we're going to get the same root. It's actually going to be a repeated root. Lambda 1 is going to be equal to lambda 2, because if this is 0, okay, this goes away, and we're just going to have negative r over 2. So we'll actually get a repeated root. All right, and this is actually interesting, where the solution will be e lambda 1t te lambda 1t. Okay, and we'll look at the general form here in a second. But then the third case, okay, case 3, clearly when this is negative, we're going to get a different form of solutions. We're going to get a similar case where it is just e lambda 1t, e lambda 2t, e lambda 1t, e lambda 2t, but instead lambda is going to be complex. Okay, so we have where lambda 1 is equal to a plus ib, and lambda 2 is equal to a minus ib. So the special solution, when we have repeated roots, okay, so for the general solution to the ODE in 1, if you recall that ODE that we were looking at, all solutions have the following form. Y of t, the solution, is equal to c1 plus c2t all the way to cj tj minus 1 times e lambda t. So the general solution here, interesting enough, is actually just c1 times e lambda t. And we see that here is just e to the lambda t. So then we're seeing that there's a linear combination for the general solution. And then here also, with the repeated root case, okay, we can see that this is just c1 plus c2t. Okay, times e to the lambda jt. All right, so this is as complex as everything gets. We see all three cases. There are no more cases than this. Okay, so now when we're looking at it, this is where it gets really excited, because we're going to start, it's going to be getting a little bit more exciting, because we're going to start looking at linear algebra for these ODEs. How can we now think of generalizing this to find all solutions? So solutions to the ODE, okay, we saw is this exponential function e lambda jt. So this belongs to the vector space of functions FRC. And what this means is that it is just the vector space of real functions to the field of complex numbers. Okay, and this vector space is closed under addition and scalar multiplication, if you don't remember. But more specifically, we're going to look at the subspace of these functions, okay? C infinity, meaning continuous functions, okay? They're functions with derivatives of all orders, okay? Infinitely differentiable. So I mentioned that this is a subspace. Let's prove it. So let's prove that C infinity is indeed a subspace of FRC. Okay. So let F and G be elements of C infinity. Well, we know that in order to prove a subspace, we have to do the 3 steps, which is first investigate the 0 vector. Is the 0 vector in? Of course, we can check that off because we know 0 is infinitely differentiable. Next, we will look at addition, so closure of addition. F plus G, okay, the jth derivative there. We know that the derivative can distribute in to F plus G. This implies we know that this here, F plus G, is indeed in C infinity. So it is closed under addition. Now we need to check scalar multiplication. So for any C complex number, a scalar C complex number, scalar times our function f. Okay, the jth derivative of that, we know we can pull out a constant. And here, if we pull out the constant, it's clearly in C infinity. Therefore, C infinity is actually closed under scalar multiplication and addition. Therefore, it is a subspace of FRC. Okay, so let's examine the linear operator that we're working with. So we define the derivative operator as the following linear transformation. D, where functions are of C infinity are mapped into itself. So we have here D, so this is just going over some of the notation. So D is going to be the derivative with respect to T. So in our example, D on Y is equal to dy dt. Okay, and the notation that we were using previously is just y in parentheses 1, and dj is actually the jth derivative with respect to t. Okay, so in example, this is going to be dj on y will be the jth derivative of y with respect to t, and we've been showing that as y in parentheses j. So I stated that this was a linear operator. Then we must prove that D from C infinity mapped to C infinity is linear. We know to show this, we only have to show scalar multiplication and addition. So let's show that. Let x and y, okay, be in C infinity, and C be a scalar, a complex scalar. Then to show closure under addition, okay, D on x and y, right, is the same, and this is just, these two are equivalent. This is just showing the difference in notation. So x to the first derivative plus y first derivative, same thing here. We know that this is just D on x plus D on y, okay, so it's closed under addition. Now scalar multiplication, D on cx, c being the scalar. We know it's just the first derivative of cx. We can always pull a constant out because it's linear, dx over dt. Okay, so we see here that c times our linear operator on y shows that it's closed here under scalar multiplication. Now I did show it only for the first, but since this is a power, we know because of the linearity of this, it would work with the jth power, so then therefore D is a linear operator. So now something that's very interesting and what we really want to investigate is we want to let S, okay, so let's just consider S being all the solutions to our ODE. Okay, then S is a subspace of C infinity. Now why would we be able to state this? And superposition principle states, we know this is true, because let y1 and y2 be solutions, okay, to the ODE. They are in C infinity, which we've shown, but then let alpha and gamma also be of the complex field. Okay, then this implies that any linear combination of these two solutions will also be in C infinity. Okay, then therefore, we want to investigate S. So then S is our solution space. So our solution space, let's just consider this polynomial p on x, okay, p of x. All right, so if we have this p of x, which is a polynomial over the complex field, if we put in our linear operator d, okay, then we are going to get this differential operator, okay, this linear transformation. Well, any polynomial of a linear transformation is also a linear transformation. Okay, so if we do this now, p of d on y, we're going to get this here, okay, and this p of d on y, if you saw right here, is also our ODE. Okay, so I'm just changing that back over to our ODE. Okay, so this is even more interesting because if we find a solution to this ODE, which we have done, and we did as an example, then clearly the solution, y, is going to be in the solution space S. Okay? But this is only true if and only if, all right, our linear operator on y is equal to 0. Clearly, because it's homogeneous and that is the solution. But this is only true if y is in the null space of P of D. Right? We know that that means that the null space, which is any linear operator that maps a function into its zero vector, which is what is happening here, then we know that it is in the null space of P of D, which implies, okay, that S is equal to the null space of P of D, which means that the solution space is actually the null space. So this is very interesting because now we know how to find the null space. Okay? So that was for homogeneous ODE with constant coefficients. I want to look at linear. I just want to show you the case when we have a linear inhomogeneous ODE with constant coefficients. Okay, so this is the exact same equation, only the right side is equal to non-zero, which would mean we would have some type of forcing. So in our example, we would have with forcing to the spring mass dampener system. So I'm relabeling this equation as 1 to make reference to it. But if we're just examining that P of D of y is equal to F, then it is no longer in the null space clearly. F is clearly, the solution is clearly in the range of P of D. So that's interesting to look at. And then also, the solution set for the linear inhomogeneous ODE, let's denote that now as S sub F rather than S. Okay, so let S sub F be the solution set of 1, this new one of the inhomogeneous ODE, for a given F equal to F. And let Z be any solution to 1. Okay? If Y is a solution to the linear homogeneous ODE, then I'm going to state that the solution space of the inhomogeneous S sub F is actually equal to the set here of solutions to the inhomogeneous plus the solution space of the homogeneous, okay? Which is equal to, so S of F, the solution space of the inhomogeneous, is just equal to, this is actually the particular solution plus the general solution, okay, where y is in the S, which is just the homogeneous solution space. Okay, so let's prove that. So here, suppose Z and W are solutions to 1, and clearly it would just be P of D on Z is equal to F, and P of D on W is equal to F. Then P of D, okay, W minus Z, because of the linearity, proves that this would be equal to 0. It's true. So then conversely, if we wanted to show this proof as well, we can show that P of D on Z plus Y clearly is equal to P of D on Z plus P of D on Y. Well, P of D on Z is F, and then P of D on Y is 0. So then this would just be equal to F. Therefore, to represent the entire solution space and every solution, it would need to be of the form Z plus Y. So let's look at a special case of our linear operator. So we know by the fundamental theorem of algebra, we can always factor our equation P of D into D minus lambda 1i, D minus lambda 2i, all the way to D lambda I. I just wanted to make that very explicit because I wanted you to see exactly why we were looking at this special case and where it came from. So P of D equal to D minus lambda I. If we look at this, then P of D minus lambda I, this linear transformation on Y, okay, is actually equal to the first derivative of Y minus lambda Y. So the first derivative of Y minus lambda y, right, we know is equal to 0 because it's homogeneous. Then for this special case, as we've been seeing, solutions are just of the form y, the solution, would be equal to CE lambda t, right? And S, the solution space, is equal to the null space of D minus lambda I, which is equal to CE lambda t, where lambda and C are in complex field. Now, this is interesting, and a little bit of foreshadowing is that we see that C, for any scalar, on E, this exponential function, is very interesting because this implies that E lambda t is a basis for the solution space to our homogeneous linear ordinary differential equation with constant coefficients. So very interesting. So let's prove that. So we need to show, though, that for a given n distinct complex numbers, lambda 1, lambda 2, all the way to lambda n, the set of exponential functions e lambda 1t, e lambda 2t, all the way to e lambda nt is linearly independent. Well, to prove linear independence, we know that we need to set it up equal to 0 and show, okay, that the linear combination of these, this is only true if C1, C2, Cn, all of those are equal to 0. If not, then it's linearly dependent. So to prove this, we're going to need mathematical induction. So let's investigate the base case together, which is not written down, but e lambda 1 t equal to 0, okay, C1 e lambda 1t right here equal to 0 would only be true. We know exponential functions cannot equal 0. So this would only be true if C1 was equal to 0. So the base case passes. So now let's consider this to be true, okay, let's make the hypothesis, the induction hypothesis, true from C1 to Cn minus 1. Okay, then to investigate this, let's do our linear operator, okay, d minus lambda ni, okay, on our function. We know 0 here, this would just go away, all right, and then take the derivative of this, right, so we take the derivative of this and we're subtracting lambda n, okay, times just this here. Now we can pull out a C1 e lambda 1t, right? So we have here C1t e to the lambda 1t. So all we're left with is lambda 1 here minus lambda n. Okay, and we do that for every single one, okay, all the way to Cn minus 1 e to the lambda n minus 1t, all right? Then what this implies is if we plug in each of these to be true, right? If we plug in each C1, C2, to all the way to Cn to be equal to 0, all right, then all we are left with is Cn e to the lambda nt, okay, because we know that this is true by the induction hypothesis, then all we're left with is Cn e to the lambda nt is equal to 0. This has to be true because the exponential function cannot equal 0. Cn must be 0. So this implies that every single element, okay, in this set is linearly independent, okay, by induction. So I'd like to recall the solutions to the overdamped, underdamped system. Okay, so this works for both. We knew that it was just two distinct lambda 1, lambda 2. For the overdamped, it was lambda 1 and lambda 2 were real. And for the underdamped, it was lambda 1 and lambda 2 were complex. So if these are solutions, okay, like we did in the homework one time using the Wronskian, checking linear independence, we should do this for this example to see if it's true for the general example that we just proved by induction. Well, if we know that this y1 and y2 linear combinations of this would then need to be equal to 0 to be solutions, then if we take the derivative of them, that combination of C1, so the derivative of this, and the derivative of this is equal to 0, then we have a system. We can set this up as a system. So here's y1, y2, here's y1, the first derivative of y1, first derivative of y2, and we have two unknowns. So these two unknowns, setting this up as a linear system, is actually equivalent. Okay, this system is actually equivalent to the determinant, okay, of this system here. And we know that if we set that equal to 0, we can then solve for the determinant. So when we do that and we solve for the determinant, we know that our exponential functions cannot equal 0, right? And since the exponential functions cannot equal 0, then that means that lambda 1, this is only true, this is only equal to 0 if lambda 1 minus lambda 2 is equal to 0. But we know that since these two are distinct, right, this only means that C1 and C2 must equal 0. Okay, because we know that the exponential function cannot equal 0. So that proves then that this is linearly independent. So then therefore, which is probably the best part, a basis for S, the homogeneous solution space, okay, the basis for S, therefore, is equal to e to the lambda 1t, e to the lambda 2t. And with that, any linear combination, we can find all solutions to our homogeneous linear ordinary differential equation with constant coefficients. Thank you for your time. Here is a reference for the book, and I hope that you enjoyed the presentation.